Hello, everyone. My name is Gabriel, and I must confess that I am heavily into cats and C++. I'm not sure which one I'm into most. I've been a software engineer at Cathion since 2012, so a few years have passed since then, and we have been creating some really cool stuff using C++ there. And I'm going to show you a few cool stuff today as well. There, I've been working mainly at Advanced Installer, which is one of our main products, built almost entirely using C++. And as I will show you in a further slide, we have um, a large code base, I would say. It's certainly not small. But also, starting a few years ago, we created a tool called Clang Power Tools, which I will also introduce a bit later on. And we will see how we are putting Clang Power Tools to use in order to make Advanced Installer even better and improve the lives of our developers in the sense that they will be able to do things that otherwise are quite difficult to achieve. Why this talk? So we love sharing our experiences. Every time we meet new people from the industry, we cannot keep our mouth shut. We want to share the things that we do and love and learn from other people to see what they have been doing. Last night at the gala dinner, I learned a very useful thing from another attendee that I'm sure we will be putting it to use as soon as we return home. So it's all about sharing, it's all about learning and growing together. And this is my second time at ACCU. The first time I'm giving a talk, I held a few lightning talks before, but a proper talk, this is my first time. And I love it here. What did we do in a nutshell? Like I said, I'm going to be sharing something practical, something that we did. I'm guessing that you, by the title, you already have an inkling of what we achieved. So I'm going to give you the numbers straight ahead. In our source code, we started with 60,000 includes just in CPP files. And we will see how we got to thinking about pruning these includes and seeing how many of them do we actually need. Maybe not all of them. Maybe we can shed 5%, 10%. But as it appears, the number that we were able to jettison to effectively remove from our code base is quite large. And we will see exactly how we achieve this. We had multiple choices. We had alternative approaches that we could take, and we chose one. Why did we do it? A few reasons. First and foremost, everybody knows that cleanliness is a good thing. It helps us, it improves our mental health. It's even when we enter a room, if that room is clean, it gives us a clear state of mind and enriches our way of being. So I think this also applies to code. We need to make sure that it stays clean. It's not enough that it works. it matters how it is, how beautiful it is, how symmetrical it is, and that we don't have dead leaves, as one could say. But we are C++ folks, so we cannot refuse some speed benefits like compilation. And this is regarding full compilation. So imagine a build system that runs a release or a debug build. And maybe by doing this, we gain something. Maybe we don't. Experiments will show. We have to measure the effect. But that's not the only kind of improvement that we can get. We can also get another improvement. Benefits that are more direct to the developer. When we change something, when we change a header, how long it takes after pressing run to actually execute a program. Some compilers will recompile translation units if they include headers, even though they don't depend on those headers. If you change them and don't have external include guards, if you have internal include guards, it will cost you. The compiler will have more work to do because of that. So this is a potential benefit as well that is direct to the developer. The first one, not so much, because a full build is not something that you do very often. Maybe we used to do that a few years ago. We had a tradition every morning when we come into work, the first thing we do after grabbing some coffee was to build from scratch our product to see from the get-go if everything is all right with it. These days, we rely more on automated build systems and not so much on this tradition. There is a saying that code doesn't lie. I think that it's not entirely true regarding includes. It can lie to you. Not to the machine, it can lie to you, to the developer that looks at that code and gets the impression that this CPP file depends on this include. It introduces that dependency into your mind, and I would say it's a small lie. So we can help erase that almost always if we work to remove these includes. And last but not least, curiosity. We cannot help our curiosity. When the question arises, how many headers can we prune? Certainly there are some that can be pruned. Now, I told you a little bit of an introduction about what we did. Now let me tell you a couple words about how we did it. Magic. Thank you for coming to my talk. Who knows this man? I'm expecting everybody, but you seem to be shy. He has shaped our ways of thinking and movies and the reaches of our imagination with his creations. This is Arthur C. Clarke, and we know he's saying about magic and the way that you cannot really distinguish it from very advanced technology. So let's work together to understand, to unravel this piece of magic that we did. So what is it? What do I mean by header pruning or cleaning up includes? In very simple terms, if we take this code that I wrote for my lightning talk 2 days ago, let's say that I'm not using the format library. I'm not using algorithm. We simply have to get rid of them so that my code will include just the things that I need, preferably if we can pinpoint this process accurately enough. So who here wants to do such a task to actually minimize their includes in the code? You're in the right room. Who has tried to do this? How did it go? Who has finished actually and accomplished it, has reached a desirable outcome? It's not that lightweight of a task. It seems simple enough when you do it on simple code. It's trivial to do, but when you actually go into production code with all its weight and dependencies and thousands of classes and files, things get much more tangled up and you are easily overwhelmed by this task. So in the next minutes, I will be sharing our journey regarding this, how we started, the steps we took along, and where we are today. And this journey has not yet reached its destination. We are still in progress of new steps to be taken. Let's take a few seconds to appreciate the scale of the task that we took. Our project is not the greatest one out there, but it is certainly large. We have 180, give or take, Visual C++ projects, 3.5 million, approximately 3.5 million lines of code, 60,000 includes only in CPP files, and it is a well established and mature product. It started in 2003, way before the modern era of C++. Some call it the dark ages of C++. But I think things were already brewing up and were on their way towards progress. Git was not even a thing. Git appeared in 2005. So we were dealing with a lot of code that grew organically over the years, implementing new features, requests from our clients, bug fixes, and so on. And we strive for 3 Gs. We want to give great value to our customers, offer our team, our developers, great tooling so they don't feel stuck in the past. And we also want great and consistent quality, that our code base is not in one part C++ 98, C++ 17 in another, C++ 20 in yet another part. So this is a challenge in C++ as the language itself evolves and we find new ways of expressing ourselves. There's also the old code that we need to carry with us. And all products have this kind of code. Not all products are fresh off the bakery, so to say. A lot of the products out there are established products with years behind them. So we need to put this into perspective, to balance ourselves in order to do this with a mature product that's quite complex. And this team, our team, has to add features, to provide fixes, to improve things, and very importantly, might not break things as they modify the code and add new one. When we write the code, we want to write it in a modern way, but in order to preserve consistency, we also want to modernize our old code. And this has proven a challenge for us, starting with C++11 and on. I was in the middle of this process because I started in 2012, like I said, at the company. So I was in there. So what we did a few years ago in 2016, we created Clang Power Tools. We saw that people have developed these amazing tools, the LLVM infrastructure, that sadly was not available to us. Our product is for Windows, the Windows platform, and it is not easy to use the LLVM infrastructure in Visual Studio. At the time, it was practically impossible. So what we did was to bridge this gap, to introduce a new product that would enable, first of all, us to modernize our code base, to bring it into the present and onwards into the future. And it worked very nicely. It enabled us to have uniform formatting of our code using Clang format. And I'm sure all of you here know the fights and discussions that are very lively around coding standards and things like tabs versus spaces that are very famous. Having a uniform styling that is automatically applied when you save the file has effectively extinguished these discussions, and this is no longer an issue for us. It also helps us to catch warnings and bugs because we are very strict with our flags. When we compile with Clang, we strive to the maximum level, W error, W all, extra, and pedantic. So after the MSVC compiling step, we also rely on Clang to give us some info about our code and if there is anything there to fix. And this can also be used directly from Visual Studio after you save the file, so right in the hands of the developer. So the timeline for us was, first of all, to use Clang format to get rid of discussions around coding standards. And we started with Clang format because you don't need any fixes to your code base. You can apply it to code that has compilation errors. It will work. It's very resilient in that way. It doesn't need code that compiles 100%. Afterwards, we did the fixes required, and this took quite an effort, and a lot of our teammates jumped in and helped us to fix all the errors that we had when compiling with Clang, so that our pipelines that we have now using Clang always pass. And when there is if an error appears there, it's only one, it's easy to pinpoint, and you fix only that. Afterwards, we moved to Clang Tidy, which was our goal in the first place, in order to modernize our code and bring it from the past into the present. Afterwards, we took Clang Power Tools towards the static analyzer checks, which we don't currently integrate in our CI/CD pipelines because they are very noisy. And these ones we run manually once in a while, so that we grab a coffee, have a few hours, look over them, and see if anything catches our eye. We have caught things using the static analyzer, and we periodically run these checks. So every time we try to modernize something about our product, we have a few goals in mind. First and most importantly, that we don't break the product, because if we break the product, our clients suffer, and they are the first priority. We want them to have the best possible experience. Afterwards, that the code remains compilable. Mostly, we are able to deal with a number of compilation errors, let's say after running a modernizer and getting 80, let's say 80 errors over a large code base, we can take them one by one and solve them. But if we get, let's say, 1,000 errors, that's a whole different beast, and that's not an option for us because it overwhelms us, and we don't want to spend that much of a time. Preferably, we want under 1 week for each modernization step to take place. And preferably toolable so that we can integrate it in a pipeline so that it minimizes the human time required to run it. So preferably if we can tool it and make it run automatically, that's great. So that it's always there, always working for us and helping us without us even knowing much about it in the background. Going forward, last year we integrated Clang Power Tools with include what you use, which is a tool not developed by us, but with which we integrate. It has been requested that we integrate with this tool, and we did just that. And we were very excited to use it ourselves on our code base. And that's what we did. We expected to get, like I said, a manageable number of errors, preferably 0, that would be great. What we got in return was something, and that's not for the entire code base. That's for a localized area, so even 1 CPP. It really, really broke things, and it was not manageable for us. We tried to tweak it to find something that we could configure so that we could increase the granularity, do something to help us grab a hold of this situation, but we were unable to do that. So we, even today, the way we expose this feature in Clang Power Tools is with the beta prefix, because we don't feel that it is ready for mainstream. There is much more work to be done in order to be actually used with real developed products. Luckily, just a month after we released that integration, Visual Studio themselves released just this feature that we needed. It's called hashtag include cleanup. And the timing could not be more perfect because it was a fresh problem in our minds. We were ready to use it. Again, we expected this, and we got this. So more or less the same problem. The experience is better, I have to say. When you open up your CPP file, Visual Studio automatically uses a color scheme to highlight the include lines that it thinks you could remove. So if the process would be much more rich, let's say, in false positives, it would be great. However, one negative side of this, it's that it cannot be toolable. You cannot say to Visual Studio, apply this to everything. You have to pinpoint every CPP file and work your way through each file, which was not something that we wanted to do. So we cannot wait. We want to try it. So we had to count our chickens, so to say. So we evaluated our approaches, include what you use with all its false positives and work that needed to be put into that. A switch to C++ modules, which gets rid of the includes altogether. The Visual Studio feature, and why not prune them by hand? because it actually works when you do it by hand. You can iteratively go through each of them and relatively quickly clean up a CPP file, because you go only one step at a time. You don't remove 15 lines of includes and then get stormed by thousands of errors. And always you can know which step you can roll back, which gives you control and granularity. And the last strategy, of course, which is always in C++, it's the undefined behavior lottery. With undefined behavior, anything can happen. So it can also clean up your includes. The problem is that the time required for such a thing to happen would have you waiting the age of the universe. So you need to be in a specific universe that helps you in this instance. And we need to make a sort of table in which we compare these approaches given the goals that we have in mind when doing a modernization step. So let's take a look at this table. As we've seen, the include what you use kind of breaks our compilation and our product. Since you cannot compile it, you cannot ship it. And it takes a lot of time from you because you are stormed by errors and you have to deal with all of them. The modules require also a large investment of time. They are the future, but today we are not yet there. If you start a project from scratch, it's awesome to go on the way of modules, but for established products, we have yet to develop a ramp for introducing modules, especially with automated tools. The same with VS include as with include what you use. Kind of breaks our compilation. Takes a lot of time to fix these problems. And toolable soon. So I kind of checked that to be green before Victor told me. So prune by hand, on the other hand, doesn't break our product because we compile it, and maybe it breaks our product. We have to test to be sure that our product stays fully functional, but we can manage that. We will see how. Takes a reasonable amount of time if you have enough hands on deck. It's not toolable. You kind of have to do it only once. So not ideal. The undefined behavior lottery is out of the question because it takes an infinite amount of time. So these were our options. We chose to prune them by hand. How long could it take? There were two of us, so more than enough hands on deck. So we estimated, we calculated doing something by hand, and it would take us around 500 days to see it from beginning to end, which isn't deal. We can deal with that. It's not an infinity like undefined behavior. So what can we do in this situation in order to make it achievable in under 1 week? It's an obvious solution. We just have to convince our boss to hire 200 more people. And everybody crunching this task. Sadly, not an option. We couldn't find 200 people. So we had to resort to automating this task, which we did. It worked. Let's see the engine of this thing. We wanted, first of all, to keep it very simple. Like I said, basically what we wanted to do was the manual pruning, but at a larger scale and in an automated way. Take each CPP file, successively identify every include directive in that file, take it out, see what happens, and then you have a choice. If it works, the compilation still succeeds, you don't need that include. If it fails, then there is something in that include that actually you need. So undo that step, put it back, and go to the next include. Run this through a loop as long as it takes, and profit. Drink your coffee, eat your biscuits, let the computer work for you, for us. So, possible pitfalls with this approach. The most scary thing that hanged over us was errors or problems that appear at runtime. Compilation issues we can deal with, they are easy to see, and you know what you have to do. But things at runtime, exceptions or functionality that changes is very scary, and preferably to be avoided. Errors at compile time, which is not a problem in our world. We can deal with them at least as we can deal with them if they are manageable in their order of magnitude. So we don't want 50,000 errors at compile time. We want 50 errors, and we can deal with them. We can make that number reach 0. As countermeasures to these concerns, we employed testing. We have an infrastructure for testing that has grown over the years, and we felt confident that these tests would help us catch problems if there are problems. Which kind of tests? Unit tests that pinpoint specific functions and code, integration tests that test our product as a whole, and also manual testing. We relied on our QA team to help us in this process so that the product appeared okay to them as well. We had a problem to begin with. You cannot automatically compile your Visual Studio source code if you have, let's say, 6,000 files. You have to compile projects. We wanted the fastest thing that could be done, so invoking the compiler itself for a specific file. But even though it is possible, it requires you to know all the compilation flags. You cannot call CLX and let it handle the compilation flags. Let's say I want to compile this file in the context of this project. You have to know everything. And we could not find a way to automate this task. So this was a blocker for us because we have, like I said, 180 projects. There are variations of compilation flags. Not these ones don't stay the same. And they are much longer than what's on this slide here. This is a sample project. So this is an issue for us, to which Clang Power Tools itself was our solution. It was able to fix this for us because the way it works, it's usable mainly from the Visual Studio IDE, but also from the command line. You can invoke it if you have an alias in PowerShell for Clang Power Tools. You can invoke it CPT here, give it the project name, and the file that you want to compile. And it will automatically take care of seeing what's inside that project, what compilation flags are to be used, and ensuring that you are able to see if after modifying this file it compiles or not. Kind of magic. It's a kind of magic, like the Queen song. Sadly, this was too slow for us. In the top right corner, I'm specifying our current estimate at the time, how long the current approach would take us to go through this process. Each call to Clang Power Tools using the command line takes around 10 seconds. Because of the overhead, this call has to load the project, translate it from MSVC to Clang, and all this work you need to do again, not simply for another CPP from that project, for the same CPP for each include directive that you want to potentially take out. So it's a problem that grows like a snowball, and this overhead was something we really wanted to get rid of. So still, we found a way. And the way was looking behind the curtains at what Clang Power Tools does. You can invoke it using the verbose mode and see effectively what does it do. It calls Clang++ and gives it the flags that we want, the CPP name and the flags. So we started thinking, let's tweak it. Let's tweak Clang Power Tools in order to make it give us this command line for each project, cache it, and do the minimal amount of work possible so that this overhead that was blocking us no longer is something that troubles us. So the steps that we had to take were to get the projects. Clang Power Tools automatically discovers the projects, get the list of them, make it give us for each project the command line that's required, cache it in memory, take each project from each file from each project and process it using the cached parameters, and repeat this process as long as it takes. And hopefully we get somewhere. Afterwards, after running some tests, we noticed that we would gain some time by using precompiled headers. So we did that. Clang Power Tools supports precompiled headers. We told it to generate them once at the beginning for each project, leave them in place, and every time we go over a CPP file, make use of that PCH and improve a little bit our compilation. This reduced our estimated time of completion to 40 hours. But still, it was better if we parallelized. So we were looking at our CPU and saw that from this potential work that it could do, it was doing only this. It was not being used to the full potential. So we parallelized. We paid for the whole CPU. We used the whole CPU. We added parallel logic to our script. And still, we noticed something. It started really well, everything at full throttle. And after a while, a fresh downturn in the metrics, and the CPU started to get stuck at 20%, 30%, something like that. And we were mystified as to why this was happening. So we started poking in and inspecting the processes and looking into what was happening, and we saw that the issue was coming from the parallel processing of the projects. So we had multiple projects and we processed them in parallel. We took this project and this project, each one was processed in parallel. The issue was that some projects have fewer files and some have multiple files. And we could end up in the case that we have CPU cores that have not much work to do because they almost finished the files from that project and are being stuck on, let's say, the last file from that specific project. And this forced us to change our approach to combine them all together. We had to do a bit of magic with the compilation parameters so that each file was given as an input multiple times if a file was included in more than one project. So that if we have a CPP that's included in two projects, we don't want in any of those projects for it to crash. Both of them have to compile after this process. So we changed our approach to parallelizing at the file level, not at the project level. We switched our approach. And this worked. Our CPUs were fully working towards this task all the time. And this process got down to around 3 hours, which we considered to be acceptable. It was something that we could work with. So we did this, make it so. We made it so. However, it took us not 3 hours, but 1 week, because we found multiple bugs and little things that we didn't see when starting this process. We let it run for 3 hours, and at the end, when we compile with Visual Studio, we see that again we are met with thousands of errors. Everything worked in Clang, but it didn't work in Visual Studio. So we had to go into it and see what was wrong so that we get rid of those issues. The script that we used can be found here. It's very small, actually. It's around 300 lines of code because it exploits, like I said, it's on a branch of Clang Power Tools. We had an experiment branch that we, like a breadboard electronic board, we stick some wires and make it give us some outputs that it wasn't officially made for. So an experimental branch that gives us exactly what we wanted. And this allowed our automation script to be very, very lean. So going to all this, when we talked about it inside our team, we were thinking that maybe a 5% reduction. We didn't know the numbers beforehand. And a few outliers, like 20% reduction, let's say, in the list of includes. But we didn't expect any performance improvement. Those were our expectations going in. The results were a 34% reduction overall from all the includes in just CPP files. So a much larger number that we expected. 20,000 includes were removed. On average, per file, per CPP file, we removed 3 include directives. And we touched 4,000 of our CPP files. Around 2,000 of them were not touched. All the includes were required. So quite a lot of changes that were happening here. Certainly a lot more that we were expecting. This is a list of, I cannot give you the specific file names, but these are files basically before our process of removing the includes, and these are files afterwards. Our top files sorted by the number of includes in each file. So the champion before all this was a CPP file that had almost 400 includes, followed by one that had 295. After the process, we can see that our champion was affected, but not by much. I can tell you that this is the same, is still the champion. Not all of them have maintained their position. Here, for example, if we look at the second place, they had a dramatic reduction. And if we interpret the data in a different way, we can also show a list of deltas sorted descendingly. The most headers the most includes we removed from a header was 211, followed by 122, and quickly dropping. From the stats that I showed you before, we saw that the average was around 3 per file. So this list quickly converges towards 3. But there are a few outliers in the code base. If we take this data and put it into percentage, we see here a file that had the champion when it comes to removal of includes. We removed 211 includes, which were 71% of the includes. More than 50%. If we look here, we found a file from which we removed 91%. Almost all of them were not required. And this list of our top removals is full of percentages that are very high, over 50%. So we expected going in that we would see a few outliers with maybe 20% reduction, but what we found was that we did have the outliers, but they were including a lot more headers than we expected. A lot more. So how is this possible? How can we interpret this data? What can we learn from it? The way we see it, it's a mix of a few factors. The first is that code bases evolve over time. They are organic. They grow. People add new stuff. And sometimes the architecture of a product inside the code gets improved. Things get reworked, refactored in a major way. But when things get changed, most of the time people will use what already works. Not many people will clean up includes after doing some major work. How many here in this room have done this? After doing something, let's say you work on something for a week, a major refactoring or rework of a feature or mechanism, going through your includes and seeing, okay, I experimented with this, but which ones did I actually need? From our experience, not a lot of developers do this. It's a natural phenomenon. So the code almost always doesn't lie. In this case, it kind of lied, because when opening those CPP files, those outliers, you would get greeted by a huge list of includes. And it lied to you because it gave you the impression that I need all of these things. I need these classes, these definitions, or whatever was in those headers. But it was not the case. They were not required. People keep adding stuff over time, but not many people remove includes. So regarding performance, after we saw that this percentage was quite higher than what we expected 5% reduction in includes, but we got 34%. So that brings into our minds the question, maybe there's something into this regarding performance. So we measured it and we saw that it does matter a bit. We see a consistent 5% improvement when compiling the code base, and we took care to balance this correctly so that it's not a statistical error. Our statistical error was 0.1% in our control group when doing 50 rounds of testing, testing the code before removing the includes and after. So this 5% improvement is now part of our lives. Every build that we do is a little bit faster. This correlates, of course, with less CO2, and it's from our point of view, it's a win. We didn't go for this. We didn't want any speed improvement, but we got some. We went for the beauty of it, for the cleanliness, to make the code more honest, to tell you actually what it uses. But there were a few dragons along the way, besides the LLVM dragon. We had a few errors. Me and my colleague Ovidio got around them. We took them one by one. It fully matched our criterion so that it wouldn't be a number that overwhelms us. It was a manageable number that during that week we solved. One interesting example was this w-undefined func template flag that you can give to Clang. We didn't use that before. We, along the years we have used Clang Power Tools, we developed a set of flags that we give to Clangs so that it matches as closely what we see in Visual Studio. But we were not aware of this flag. During the refactoring, we found that we had to do this. It's a complicated thing to explain, but we regarded it also as a win. We were not aware of this flag, and it makes our compilation even more able to detect problems. We also had some issues at link time with external variables. When we invoke Clang, we don't actually build something. We just call the front-end compiler, and there is no linking involved. So this step was not able to be this problem was not able to be identified using our Clang compilations. We saw it when actually building the product with Visual Studio. But like I said, me and Ovidio fixed it, and all was good. And also we encountered some funny bits regarding macros, which are a lovely feature of C++. We had macros for debug 64-bit that posed some challenges for us. In order to quickly go through this, we didn't bother about 34-bit and 64-bit. We started with 32-bit. And there was some code in the if-defs that were guarded with the x64 that were not taken into account by Clang because we were not compiling that code. We were compiling the 32-bit code. So we had to go over these changes and fix them as well. So after going through the macro bits and fixing them, we were all good. No more dragons. So the team was quite happy. We actually held an internal presentation regarding this a few weeks after the changes were done. Meanwhile, the testing, like I said, we were relying on our tests and the QA team. Everything was extra checked to be sure that nothing bad happens. And we were not able to find anything horrible with the application. Nothing escaped our testing layers and all was good. People were very happy. So much so that they were asking even more of us. They were asking us to not just remove includes from CPP files, but why not remove them from headers themselves, which is a task that's a bit more trickier and we are currently working on. We are almost there. It's a bit trickier because you cannot compile a header. You have to find all the files that use that header, which we do. That's a solved task. We still have to balance a bit the compilation workflows so that we can, like I said, get some results in a meaningful time span. And we also are working towards integrating this whole process in an automated pipeline that will run once a month. So not a nightly CI pipeline, but once a month. It looks to be good enough for us. What's next also, like Victor said, and I have a lot of hopes for this, we hope that Visual Studios include cleanup and include what you use. Get to this. We don't want to be doing this kind of automation. We would prefer not to do it and let the tools work for us. And we are keeping an eye on this. And as soon as we will get here, we will embrace it and we will be using that. For now, we are not yet there. So we learned a few lessons from this journey. We learned again that our code base is evolving, and sometimes, like in natural evolution, there are some things that become vestigial and are not actively used, like let's say our appendix. We can strive to identify these parts, and if it is safe to do so, why not remove them? And this kind of task is best to be done with tooling. If you don't have the automated tools to do it in any mature product out there, you will not be able to do it. You will need 200 more people employed at your company to do it. So don't be afraid to experiment with tooling, even your own tools like we did. We poked it and prodded it and made it do things that it wasn't designed to do, but it got the job done. So many people are afraid to do these kinds of tasks because they don't want to break things. So always have testing infrastructure with you that will empower you. It will give you courage to change things, to improve things, which you would otherwise be not so willing to touch. The resources, like I mentioned, Clang Power Tools, our open source project. This QR code leads directly to the experiment, to our experimental branch. You can also find us on the Visual Studio Extension Marketplace. And why not give it a try? This concludes my content, and if there are any questions, I will be more than happy to address them. Thanks.